There we go. All right, that's good timing there, recording. Didn't need you to capture all that in its glory. All right, let me see. Boop, boop, bum. Come down here. There we go. All right, I do have a question. Oh my goodness. My computer has decided to go insane. So I do have a question from section 9.5. I think this is the same one I was just talking about. Let me share this. So the section 9.5, number 36 and 39. Yes, that is pretty much the same area. All right, so this whole section, just ignore where they say exactly, because it's kind of dumb what they did. But I mean, you got decimals. There's no way to get the exact one on some of these. 36 is one. It looks like you should be able to get the exact one. Are you just not sure what to do? Oh, and 33. So 33. So again, every single one of these just about involves identities, right? So some of these identities should be jumping out at you. 36 and 39, they involve the same idea. I don't know if that helps. Does that help at all? There are examples in the section. Can somebody tell me there's two things that are bad about 39? One of them is really, really something we've hit a couple times. So can somebody tell me one problem with 39? Just to focus on that for a minute. Sure, I can do an example, but I want to give me this one thing.
The angles.
Tell me. Go ahead. Sorry.
The angles are different.
Yeah, angles are different. Bam. So you're gonna want to use. So let's do 38. Let's try out number 38. Shwa. So the very first thing I want to do is rewrite this. And of course, there's only one way to do that. So how do I rewrite sine of 2t? Oh, this is going to be remarkably boring. Hello. What's the formula for a double angle for sine? Sine of 2t is 2
sine t cosine t.
Yes. All right. This is not Jeff being an asshole. This is just Jeff saying, hey, I told you a while back, you have to know this shit. So at this point, you should know that. Right? I mean, it's just, you know, you're going to have to memorize something. Every math course, it's not all memorization. It definitely is not all memorization, but it is some memorization. Now, some of you guys are like, I don't want to say it because it's too easy. I don't know. Now, the thing to be careful about, instead of knowing how to spell cos, what would be the next step on this problem?
Divide the cos.
Nope. And the reason is, what would be the next step on this problem? It wouldn't be to divide the x, because then I lose an answer. It would be subtract the x over and then factor. Now there's a way around that. There's kind of another way to do that. But that is the way to be extra careful if you're not sure what the hell else to do. And blah, 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 who cares about that problem? So here I'm going to subtract cosine, and then I can factor, right? Are you guys with me out there? And then I can solve each of these little mini equations, right? Is that cool? You guys with me? I think the problem is, all right, problem is, it's been a while since we talked about this section, and some of you guys are just now starting this section. So I'm trying to be a little lenient with due dates. And I understand some of you guys can't do as much homework all the time as you'd like to. But at the same time, it's I think I've been pretty good about identifying content on the videos I upload. Somebody asked me a while back to try to do a good job of that, and I'm trying. You should be able to find the video about when we talked about this. Now, obviously, I can do examples if you ask me to do examples. I'm not going to spend a ton of time on it, though, right? But it's been a long time between when we discussed it and when you're doing it. And that's normally not the best way to do things. Is anybody not clear on what motivated me to do each of these steps so far? It's very similar to what we do with just variables. And now I can do my solve these two little equations, right? Let me just cut to the chase here. Add the 1 divided by 2. Right? Is that all right? Yeah, okay. And this is one that said, get your answers between 0 and 2 pi, if I remember correctly. So now you can just figure out what angles make cosine 0 and what angles make sine 1/2. And that's not a big deal. Okay. Is that all right? Is that all right for an example? The difference between, the reason 39 is a little more difficult at first is because of this guy. What's weird about this guy? And again, cosine's an asshole. And here's another example. How is cosine being an asshole with this identities? Well, I gave it away there, but with the cosine of 2t, how many options are there for how to rewrite that? There's 3 options for that. And I'll tell you right now, you're going to want to use the one that involves this guy and only that guy. There's an example, I think, exactly like this in the section. All right. Any other ones of these that jump out at you that you want to look at? Anybody? Does anybody have a? No? Okay. Here we go. Here comes somebody. 34. Okay, let's see. So let's look at 34. I'm going to clear all this stuff away. Bye. Oh, shit. I did too much. There we go. 34. Oh, okay, okay. Oh, here comes the chat. Could you go over number 50? Oh, okay. Hold on to that idea. Okay. So look at 34. What is this related to? And if you don't like the way it looks, just rewrite it. Say sine of something times cosine of something else minus cosine of the first something, sine of the something else. Okay, that looks like something I'm supposed to know, right? Maybe? Maybe. What identity is this related to? What does this become? Sine, cosine, sine, cosine.
The sine of a plus b. Sorry, a minus b.
Yeah, remember sine's the nice guy. Give a turn, and then he keeps the sign the same, S-I-G-N, right? Sine's the nice guy. Cosine's the asshole. So now you know how to rewrite this. You know what A is. You know what B is, right? You guys, is that part of the sticking point, or have you already done that and you want to know what to do next? Is that the question? This problem, to be honest, let's do another step. So this would be sine of negative 5x equals negative 0.1. Is that cool? Oh, here comes a chat. Okay, no worries. So everybody with me so far? Just using so A is 6x and B is 11x. So I get sine and negative 5x. What is sine and negative angle?
Negative sine 5x.
Yes. So then just these two negatives cancel. Is that cool? Just can kill those two negatives. Is that all right? Okay. Okay. Pop. And now I pretend like, so this is sine of some angle equals 0.1. So this is really dumb. So what is the angle equal to? Well, how do I kill sine? What do I do to both sides?
Inverse sine.
That's right. I thought somebody was going to say silver bullet. No. Sorry, that's for a where sign. And then you get divide by 5 and you get this thing. Now the thing I'm forgetting is, all right, let me before I go to this step, this one's kind of dumb. I agree. But that's just the way it is. if you do put inverse sine of 0.1, you get some funky ass answer. If I wanted to capture all of the answers for this, what would I have to put back here? Plus or minus what? We're talking about sine. All right, maybe it's a good idea. Let's do an easier problem here. What if I had sine x equals 1/2? What's the basic angle we're talking about? What angle makes sine 1/2?
Pi over 6.
Yeah. So I'm not sure what's going on. Do you guys just not like talk to me anymore? Or do you actually not know? Or what's going on? I'm a little concerned. At this point, we need to know the basic angles. We have to know them. You have to. I tried giving you multiple ways to think about it. I don't know. Maybe everybody's just being really quiet. I have no idea, but I'm concerned. So how do I write that in radians? Oh, I think you said it in radians. I can't even remember now. Yeah. So pi over 6. I like it. And why does that make sense? Because sine is small. Sine likes y. So I must be far away from the y-axis. That must be 30 degrees, which is pi over 6. Okay. Plus or minus what?
Two pi.
2 pi.
Theta.
Okay.
No.
X.
Okay. And then you get another answer. This is where this is going to be a little bit freaky. Where's another place that the sine is 1/2? There, right? That's another place where sine is positive and it's only 1/2. So that would be 5 pi over 6. That is pi minus pi over 6. That would be 5 pi over 6. Do you guys see? And again, we've done all this. We did a lot of these. It's just been a while since you did them yourself. I'm hoping this seems familiar, possibly. So then what do I have to be careful about here? There's a whole other option where it would be pi minus inverse sine of 0.1. Plus or minus. So now we know it's 2 pi k. And why is it 2 pi k? Because if I go around 2 pi, I pick up another answer. If I go around another 2 pi, so k would be 2, I pick up another answer, blah, blah, blah. Okay, maybe.
Had the
Right,
pi,
sir?
was that tangent? Which
Say again,
the
sorry?
question had the plus or minus, it was just pi. Was that tangent?
Yes. And why does that make sense? Because what's the period of tangent?
Pi.
Pi. And the period of cosine and sine is 2 pi. Now, of course, we saw a couple of situations that I showed you where you could write a couple of these in more compact terms, and this would become pi k sometimes. If I had the option of answers that were exactly across from each other. And again, we went over all that. It's just been a little while, right? Okay. Let me see. Is that all right? So now 33 is going to work very much the same way.
Aren't there 4 angles though on the unit that would give sine? Oh wait, no, that's positive 1/2. Never mind. Got it. Gotcha.
Yeah, if it was if it would have come from a squared thing, then it would have been plus or minus. Yeah. That's where we got the option to rewrite some stuff more compactly.
Can you
Okay.
explain how you got the pi minus sine inverse? Or
Sorry?
how the second answer that you wrote, the 5x equals pi minus the inverse sine.
Okay. So that's just realizing how we got this answer. Are you cool with what we did over here? If you're not cool with what we did over here, then you're really not going to understand what we did there. See, everything builds on each other. So if one answer, so again, let me pull this down here. Let me write this in a different color. Bam. So if I have the equation sine x equals 1/2, it either happens at 30 degrees or it happens at a reference angle. Crappity doodah. Jeff, that's very good. Or it happens at a reference angle of 30 degrees. And what would this actual angle be? Pi minus, where'd it go? Pi minus pi over 6, because it's back pi over 6. Do you see that?
Yeah, that makes sense. Thank you.
I like it. You're welcome. So that's the generalization we can make. The gross thing about these problems here is they are going to involve inverse sine expressions, which is just weird to work with. So then we really have to stop and think, how would we get another answer if we knew like a base answer? Which is then we have to do exactly that here more explicitly. Right? You didn't think that way when you looked at 5 pi over 6. If you were with me back there, you got 5 pi over 6. You didn't think about it like pi minus pi over 6. You didn't think that explicitly about it. But when you got inverse sine of shit, you got to think more explicitly about what you do in general. Okay, maybe. So this is why, all right, so I don't know, maybe I should add a more general discussion about homework earlier. Even if you're way back in homework, the night or the day after a lecture, I'm going to go try a couple of problems out in my notes. I'll leave a little space for practice problems, do some problems from homework in my notes. And then when I go to do the homework, I can go back there and look at what I did, just so I got my own practice with the idea. So it gets in your head, right? Just sitting here and listening to me spew my stuff is not going to make it in your head. It isn't. That's why we put homework, so you get some practice. Anyway, sorry. Some of you guys don't need this, but some of you guys, I don't know. That's why this is going to be difficult, because it's been a while since we talked about it. Anything else from homework stuff that I missed? I think somebody had a question for me. 54. Okay, so let me clear all this stuff away. Yeah, look at 54. That's gross. All right, so let's see here. Yeah, it's not bad. Okay, I can do that. So let's see. Here's the problem. So there's a couple of gross things happening here. So it says look for trigonometric identities, right? So I've got 2 tangent x over 2 minus secant squared x minus sine squared x. And this is not proving an identity, right? This is finding solutions. This is solving this equation. They're not saying that one side always equals the other. Okay. So sometimes it's easy to get those two mixed up because you do so much of the freaking verifying identities. You get sort of in that mindset. But what's a connection between these two guys, just to start things off? Is there any connection between those two?
They both have a denominator of cosine x.
Yeah, and since this is solving an equation, right? Since I'm solving an equation, this is something else. With identities, I'm not allowed to move things to other side because that would be assuming the equality was true. But here, the equality is given to me as true. So I can do something like this. And why is this kick ass?
Because it equals 1.
Shit, yeah. And then let's see what happens. This will be 2 sine over cosine over 2 minus 1 over cosine squared. I mean, this is just a suggestion. So if I multiply top and bottom, anyway, I'm going a little too far. So you guys start to see, if I multiply top and bottom of this by cosine, that'll kill the internal fractions. Then I can actually multiply the bottom up to this side, right? You guys follow? So I think it's very possible that you're so used to doing identities, and I think I've seen this happen, that when you get to solving equations, you feel more constrained because you don't realize it's an equation. You're allowed to move shit around now. Thank the gods, right? It's not verifying an identity. Does that help anybody, or is that not really what's troubling anybody? I have no idea. Or has anybody tried this? All right, Doug has given me some kind of signal. Oh, thumbs up. Okay, good. Is that enough for that problem? Whoever asked me that question, is that enough to get you going? If not, just say so. Okay. All right, how's everybody else? I think I got all the questions that people asked me so far. Everybody else is okay?
When is the chapter 10 test?
I don't know. Let's take a look. Let's take a look at. Oh, I got to spotlight myself because it's all about me. Hold on. Let's take a look at the. I can't speak. I'm gonna give up. I updated some stuff in Canvas. There's words. So if you look real quick, I'm sorry. The homework sheet's updated. So the question was, pay no attention to the edit to the formatting. Just leave me alone. So our next quiz, of course, is today, but the quiz on chapter 10, they're going to be November 12th and November 19th. Is that really the way it's going to be, Jeff? Sure, why not?
But
yeah,
buddy. On Wednesday,
that
right?
seems soon, doesn't it? Doesn't that seem soon?
And we don't have class on Wednesday, right?
We sure don't. That's right. I don't know why I'm affecting this tone. I'm not. Sorry. So I'm fine with moving this back. That's fine. I might have just had that date and forgot to change it. Let's see. Well, it makes sense. I'm trying. I think you guys are understandably to a point falling behind in homework, but that's kind of killing you with connecting what we do in lecture to what you're doing on your own. Yeah. Okay. So I'm trying, if I push these too far back, that's just going to allow you to do more of that. But I'm fine with, let's push that back to the 17th. How's that sound? And then I'll push this other one back. So I have to update the damn thing again. Sure. Let me see. Somebody's chatting at me. When is your final? Finals set. There. Bam. Bam. All right. Well, okay. That's the way it is. Just to remind you guys, do you guys remember how many credits this course is? How many units this course is?
6.
6. Holy shit. So basically it is homework equivalent to 2-3 unit courses. And to be really honest, I've cut my homework back from what I normally do just because of the times we're in. Am I trying to make you feel bad? No, I'm just trying to make you realize this is the way shit is. Let me see. All right, let me make a note of this. Let me make this official on this video, at least. So we'll change this to the, what did I say, 17th? And we'll change that. Shit, now I can't even see anything. Here we go. Let's see, 19th. Oh, I see what I was trying to do. Oh, I remember doing that. I try to make everything on a Thursday. Thursday makes grading easier. But I didn't go back and change it after anyway. So let's make that. I have Thanksgiving start on the 25th, just because, in case anybody's actually going to go somewhere. The traveling normally happens on the Wednesday, right? So I always hated having classes on Wednesday. It didn't make sense to me. So let's do that on the 24th. All right. And then I'll have tons of time to grade that one. Jeez. All right. Now, see, I want you guys, and now listen, I have no idea if you consider me to be an asshole or something with the amount of homework I expect and how I react when you ask a question about it. But I am completely open to suggestions about changing due dates, changing dates of quizzes, whatever. Obviously, we've done it a couple of times. So there's nothing wrong with asking that question. If you cannot do every problem in homework and you are falling behind, start doing every other problem I assigned. I thought, have I not had this discussion with you guys? Make homework your own. Homework is there to help you get ready for graded assignments. The homework cannot hurt you that much. If you have to do every other one to keep on pace, do it. It's your class. It's your education. Why did I assign the problems I did? Because I think you need to do them to get enough repetition to get it in your head. If you don't have the time for it, you do like I did in college. I took the hit on my homework grade and I focused on getting ready for the tests, right? So I kicked the tests ass and then I would do horrible in the homework grade. Oh, well, that's how I ended up with a lot of personality on my report cards. Because like a lot of you guys, I was working 3 jobs. I was working 3 jobs, going to college. So, you know, I'm sorry, I'll stop ranting. I was walking uphill both ways. The final, like I've said before, the final will require a camera. The final will be taken during the final exam time, during these times, 6:05 to 8:05 p.m. And everybody will be on camera. It's going to be really exciting. I'm going to love it. 2 hours of me just looking at you. It's going to be awesome. Or maybe I'll record myself as if I'm looking at you and then I can go do other shit. It could be me or it could be a recording. So you never know. Take your chances. Is that all right? Are you guys all right? I really hope you guys don't take my joking tone as not taking your concern seriously. It's never what I mean. I'm full of rants. I'm full of some stuff, and rants is one of them. All right. So let's see where we left off here. Any other questions from chapter 9 or maybe even chapter 10? I don't know. I love you guys. How many questions on the final? I don't know. Normally my finals are anywhere from 20 to 30, somewhere in there. And I'm counting A, B, C, D, right? I mean, that's as much as you're going to get out of me right now. Yeah, I don't know. So if you think I don't give you enough time on tests, you will think I didn't give you enough time on the final. Oh, well, it's just the way things are. I don't purposefully make that happen. It's just, Okay. Anything
And
else from homework, guys? Sorry.
I was just going to say the final is cumulative, correct?
Yeah. Finals every damn thing.
Okay.
So I don't know if you guys noticed this, but I built in 2 review days and I will have a practice final exam. Yes. So that might help with questions to ask on the review days. I might even make, oh shit, do I want to say this? If somebody reminds me, I might even make like what I like to do is I make like a concept outline. Because when I studied, listen up, real talk kids, when I was in college, I studied to the point where if you told me, you said some idea, I could tell you what section it was in. Do you understand? I didn't do it for that purpose, but the way I studied, it just was a byproduct, right? Yeah. So, and I would rewrite all my notes. It was insane. Yeah. Anyway. So y'all don't have to be as large of a geek as I am, but you have to be somewhat of a geek. 45 on 9.3. What do you mean if I don't mind? Can you guys see the book now? Okay, thank you. All right, let me see. 9.3. 45. I feel like I have to, like every week or so, I need to have a discussion with you guys about, I love questions, I love suggestions, all that kind of stuff. Number 45. Oh yeah, okay. I'm pretty sure we did one sort of like this. This is a, you could say it, Jeff, an identity we don't have to know. I feel like I almost remember it. So this is, I don't make you know this identity, which of course is this identity. This is tangent squared, right? And there's an identity for tangent squared. And I feel like it's 2 tangent over 1 minus tangent squared? Or is that tangent 2x? Shit. What's the formula for tangent squared? I don't remember. Oh well. But you'll have it on your sheet back here. Are you with me out there? So again, like I told you, the ones that I don't personally have memorized, I will not make you memorize them. So there it is happening. Where's my trig? Is this it? I really need to rename these things. Oh, no. It's the one that says memorize stuff. Yeah. Here we go. Trig laws. So it's below the black line. So it's one that you didn't have to memorize. Tangent squared. Oh shit, did I even put it in here? Or is it up here? Oh, I didn't put any of the squared stuff in here. That's right. So you have to get it from there's tangent 2 theta. I remembered it. All right, sorry. So you have to actually get this from the section. So let's see. Tangent squared. There you are. Tangent squared. There it is. That's really gross looking. That's after they've done tangent squared for real. Where's tangent squared for real? There it is. All right. Yeah, I totally didn't remember that. So tan squared is 1 minus cosine over 1 plus cosine of double angle. Which problem is this again? Shit. Here we go. Okay. Yeah, okay. So here. I got to do this quick before it goes out of my head. So let me write this real quick. Tangent squared is 1 minus cosine 2x over 1 plus cosine 2x. Okay, I just want to write that down real quick. So this is tan squared, which is basically what you have to do. Every time you see a fourth power, you have to rewrite like this because I do have a property, I do have an identity for this. So that's going to be 1 minus cosine 2x over 1 plus cosine 2x squared. And then you do have to FOIL out the top and FOIL out the bottom. And then you're going to have to use cosine squared because you're going to have a few cosine squares. Are you with me? So these do involve a couple of levels of work, but some of it is just freaking foiling shit out. And then the other one is looking up. So eventually you're going to get cosine squared 2x a couple times, right? So you have to look up the cosine squared formula. Are you with me out there? Let me see. Okay, good. I'm not saying these are straightforward. I am not saying that. I am saying that you have, you can look back at the identities, you can look at the ones that they give you in the sections. You don't have to try to do the homework in a bubble, especially the tangent shit. I didn't make you memorize a lot of the identities for tangent because they're just so freaky. And I don't need an identity for tangent 2x. I can just get it from sine 2x over cosine 2x. 36 on 9.5. I thought did we talk about that? 36. No, we didn't. Okay. Oh, wait, this is 9.3. So 9.5. Yeah, we did talk about that one. Yeah, okay. So my hint there was, like I think it was Jason pointed out, the angles are not the same. So there's no way in hell you could solve an equation where they're that level of unlike terms. So use an identity to rewrite this. Do you see that? Are you out there? Okay. And then you can factor it like normal. And you get your two little equations you solve. I like it. Okay. All right. Okay. So something you're going to need in chapter 10, just to remind you guys, is the polar graph paper, Jeff, really? Be very, very quiet. Let me see. Polar graph. Here it is. Blank polar graph. So I gave you this. If you don't like what I picked out, You can Google polar graph and you can make your own polar graph paper. It's fine. I just wanted to put this up here so you have a quick way to get it and print it out so you can do those problems. So you want to have that you can access. And I think we did, oh shit, I don't want to look at section 3.6, go away. We did do this. Will you stop it? I think we did this. Yeah, we did this in a past class. Might have been the last class. Or we did this. We just haven't done much with this side yet. That's what we're getting into tonight, is this side here. All right. Okay. Let me see. Let me reset here. So as long as there's no other questions, what's happening with this? Hold on. Somebody's emailing me if there's class. Are you here? This is weird. All right. All right, sorry. All right. Bam. Don't think she's using. No, they're not here. Okay. All right. We'll find out what happens. So last time we did graph a circle. We did an amazing job. We graphed a circle. The reason it was amazing is because we did it in polar units, polar coordinates, right? So even though it's a simple structure, it's a simple shape, the way we did it was very different than what we're used to. So tonight we're going to do something a little more complex. And actually, let me do this the other way around. Let me go ahead and show you this here. This is kind of neat. Let me see. First off, I got to make it. Where did you go? Are you over here? Yes, you're over here. Okay. Bam. Bam. Yeah, let's do this one first. All right, I got a couple things I want to show you. So this one is kind of nifty. This is that Desmos thing I was telling you about. And one thing you can do in Desmos is you can create these sliders. So look at this equation up here. So right now I've got A and B set to 0. Can somebody tell me if I had an equation R equals 2, R equals 2, what is that the equation of? What does R mean?
Vertical line.
No. What does R mean?
Circle with the
A
radius.
circle. I love it. I know what you're thinking about. The person that said vertical line. Y equals 2 or X equals 2 would be a vertical line. And that is because X is a constant and it doesn't care what the other variable is. So the other variable takes on all of its values, and every time it takes a different value, X is 2. So that's why it's a vertical line. Are you with me? This is a perfect segue. If I make A 2 and I keep B 0, I'm going to get R equals 2. There we go. And I get this little circle. Woohoo! Right? You guys with me? That's kind of nice, isn't it? That's nice. And again, it makes sense. What variable is missing if I have R equals 2? Theta is missing. So theta can take on any value it wants to. Oh, I can do this shit. Wait a minute. I can incorporate all kinds of shit here. Look at this. I just realized. So theta can take on any value, and every time theta takes on another value, R is 2. R is 2. R is 2. R is 2 here. R is 2 there. What about here? Oh, it's 2. What about over there? Oh, it's 2. Right? So it's, do you guys understand what I'm saying? So that's, since our coordinate system is circular, the equivalent of a straight up and down line is now a circle. It does the same thing. It's actually the same reasoning. It's just everything's been bent around on itself. I love that shit. All right. So now watch. What the hell's going to happen if I make B something that's not 0? Well, how's my poor little circle going to change? Poor little circle. Well, let's see. Let's try to make B something positive. Let's make B There we go. Look what's happening to my circle. Look what's happening to my poor little circle. All right. Now, before I get too far with that, let me make A 0 again. Who remembers what R equal to something cosine theta creates? It creates a what? Like R equal to cosine theta. What would that create? Does anybody remember R equal to cosine theta versus R equal to sine theta?
Aren't those the X and Y coordinates?
Oh, I see what you're saying. If it was
Yeah.
R cosine theta, it would be X. But now I'm saying R equals to
Oh, okay.
cosine theta. Does somebody remember what shape that makes? Well, let's find out.
Was that the butt graph?
No, it's a circle. It's just a circle on the x-axis. So if I had a sine here instead of cosine, it would have been on the y-axis. So when I make A2, I get a circle, but when I make B2, I'm going to add in another circle on top of that. So that's some weird ass shit. So what I realize, well, let's see, how can I say this? And just to show you a couple of things about this, and then I want to show you a different way to think about this. So why does this make sense? Look how far out it goes over here. It goes to 4, doesn't it? And that only makes sense because I've got a something that goes out to 2 plus something else that goes out to 2. So of course it's going to go out to 4. Now, why does it go to 0 here? Because one of my circles is over here. So it's pulling everything in this, oh, get out of there, in this direction. It's pulling everything over this way. So you can imagine, look what if I make, what if I make B negative? Oh, interesting. What if I make B -2? Hey, look at that little butt graph. All right. Now, what if I make, now see, if I stay within 0 to 2 or -2, it does that kind of thing, right? Now let's see what happens if I go beyond. Oh, look at that thing. Look, it's got a little baby. Oh, it's a little baby. Baby's getting big. Oh, geez. All right, you guys semi with me out there? Now this is not explaining why this is happening, but I want to show you the Desmos thing. It's really cool. You can create these little sliders. And if I zoom in, you can really see this thing kind of come create itself. Let's see. Oh, shit. I try to make you slide better. Oh, well, too bad. I guess I didn't. Oh, well, too bad for me. All right. I want to show you one other thing, a little animation. I don't think there's any noise here, thankfully. Here's another way to look at the creation of this cardioid. So I've got a circle. I got one circle of radius 1 and another circle of radius 1. Do you guys see that? They're both the same radius. So I'm following a point on the circle as it rotates around. Now watch, it's going to become at 4. Bam! See how they both added there to get to 4. But watch how it comes internal, and now it's on the other circle. And that's why you get that little 0 part here. So it becomes additive back here, and then it becomes subtractive in here. All right, maybe. So that the radii of these circles are the coefficients. Let me come back to this other dude. Thank you there. So if I make them both 2, that's why the picture looks like this. The minute those are not both the same number, now each of those little circles with the one going around the other one are of different radii, which is going to affect how long it takes this guy to rotate. And that's why you get these different effects. That's why you get stuff like this and stuff like that. Okay, maybe. If they're not the same number, that means the radii of the 2 circles, get over there, are different. If they're the same, it makes that nice little right at 0 little meeting point. If they are different, that's not going to meet up right there. Okay, I think maybe you guys kind of get that a little bit. Are you ever going to actually have to do this type of thing yourself? No. These are really neat. A lot of these images we create, you can think of them as circles moving around other shapes. And this is one of the most basic ones, a circle rotating around a certain other circle. And we're keeping track of a point on that one circle that's rotating, right? It's really interesting. Does it help you construct the graph? Not really, but it's good to see. And then this helps you. Remember that spirograph game I told you about? And I think a few of you guys indicated you knew what I was talking about. The little gears. That's this. That's this. Just with more gears possibly. And differently shaped gears make different things happen. Oh, this is exactly what we're talking about. Okay. So let me reset again. Let's try to actually do a graph of something. Let me see. Let me pull up Scheisse Meisse. Let me pull up that blank polar graph paper. Holy crap. All right. There we go. Blank polar graph. Bam. So hopefully, I don't know. I asked you guys last time to have some print. I don't know if you printed out any more for today, but let's see what happens. So let's try to graph. We already know what this should look like, but let's try to graph. Let's do 4. No, Jeff. Let's not go crazy. Let's do 2 plus 2 cosine theta. And then I want to see if this leads to some motivation for what we're going to look at after this. So the way to do this is to make a table of values. And when we make an R theta table, it's kind of silly because our inputs are over on this side now, but oh well. So if I start at 0, what do I get for 0? If I put a 0 in here, what's cosine of 0?
1.
1. So you get 2 times 1 plus 2 is 4. So there's that additive part, right? That's when they go out to 4. Then let's try pi over 6. And again, when we do this, we're going to round it to 1 decimal place because we're doing this by hand, right? So cosine of pi over 6 is rad 3 over 2 times 2 is rad 3. So what is 2 plus rad 3 rounded? I always forget that. Is it 3.7 or 3.5?
3.7.
3.7, okay. All right, you guys keep going. Do pi over 4, pi over 3, and then pi over 2. Do those. I'll sit here and wait. Oh, I am really silly. I swear to God. You guys have that copy down, right? I'm gonna start this over. I always use the wrong editor. I love it. All right. So let's see, cosine of pi over 4 is rad 2 over 2 times 2 is rad 2, which is about 1.4 plus 2 is 3.4. Whew. Pi over 3 is nice, right? Cosine of pi over 3 is just a half. So half times 2 is 1 plus 2 is 3. And then cosine of pi over 2 ain't nothing. You ain't nothing. All right. Now, I could tell already that I need to go a little further, right? So if I do 2 pi over 3, and then 3 pi over 4, and then 5 pi over 6, and then pi. Right, what really matters is I can really just focus on the denominators because the reference angles, but I know that the answers for cosine will come out how for these angles. I'm now in the second quadrant, so they're all going to come out
Negative.
negative. Yes. So it'll still be, so pi over 3, cosine pi over 3 is still a half, but it's negative a half now. Twice negative a half is negative 1. 2 minus 1 is 1. And then 3 pi over 4 will be rad 2 over 2, but it'll be negative. So it'll be 2 minus rad 2. 2 minus 1.4 is 0.6. Jeff, can you, oh my God. All right, Jeff. Either I didn't take all my meds or I took too many meds. Pi over 6 is going to be rad 3 over 2, which is in the negative. So then 2 minus rad 3. Oh, come on, Jeff. Why can't you remember? So that's going to be 0.3, right? I believe. And the cosine of pi is negative 1 times 2 is negative 2 plus 2 is 0. There's the thing coming down, wrapping around on itself, making, you know, the upper cheek of our butt. All right. So if I want to graph these, right, just to remind you guys, so to graph this point, I face this angle and I go forward 4 because it's positive. So 1, 2, 3, 4. I don't think you can see my cursor when I do that. So 1, 2, 3, 4. So I put a dot right there. And then I face this and I go out 3.7. So 1, 2, 3.7 will be about right there. Doesn't have to be perfect. Just make it a little further than halfway, right? And then you just keep on going. This is, I really hope to God some of you guys don't just see this as busy work or just work or whatever. It's kind of flipping cool, especially when you stop to think this is the XY plane wrapped around itself, right? It's crazy. I don't know. Might be just me. So pi over 3, you face pi over 3 and you go out 3. So let's see, 1, 2, 3. And pi over 2, same thing. You face pi over 2 and you go out 2. So 1, 2, pop. And then just continue. 2 pi over 3, we're going to go out just 1. It's coming in fast now. 3 pi over 4, you're going to go out 0.6. Oh boy, a little more than halfway. And then 5 pi over 6, we're going to go out 0.3. Oh, Jesus, it's really in there. And then we're at 0. So it goes here. Oh, crap. Jeff, it was looking good there for a second. All right, let me see what I can do here. Goes around. All right, not too bad. Now, here's the motivation. You already know from the animation we did that it's just going to repeat that upper part, right? It's just going to be, you know, basically this, right? What kind of symmetry would that be? Symmetry with respect to what?
Are you meaning like reflection?
Yes, but symmetry. Remember symmetry? It's like, where is the mirror? So you're right. It's like a reflection. Go ahead. Sorry.
Symmetric about the x.
I love it.
Symmetric.
But go ahead. Sorry. Yes, you're right. I heard you. The problem is we don't call it the x-axis anymore because this ain't no xy plane. We actually call this, I was going to make a dumb joke. Like what else do I do? Polar, not the Polar Express. There it is. It's the polar axis. That's what we call the x-axis in polar coordinates. It's the polar axis.
What's the equation for the polar axis?
Ooh, I like it. I might want to make that as an extra credit. Because this, well, to be really honest, it's not that difficult. I'm about to give it away though. Because I want to transition this into a discussion about the different types of symmetry. And the second type of symmetry involves saying this guy's equation, the equation of this line, the equation of the y-axis, right? You know what the equation of the polar axis is. You do. What is the defining quality of the polar axis? There's actually an infinite number of ways to say it, but there's a base way to say it. Anything that's on the polar axis, any point on the polar axis, what's the same for any point? Let me go down here to this one. Let's get a fresh one. So any point I put on the polar axis, what's the same about them? What angle am I looking at? That's why there's multiple different answers, but am I not looking this way and then going out any number of r's that you want, any amount of r's, right? Or I could go negative r back, but I'm still looking in this direction, right?
Angle
So
zero.
does somebody have the equation of it? Sorry?
The angle 0.
Theta equals 0. I love it. So what's the equation of the y-axis?
Theta equals pi over 2.
Exactly. And that's a boring axis. For some reason, that's not given its own name. We call it the theta equals pi over 2 line. Right? I don't know why. But let's focus on this. All right, I really want you guys kind of with me. So this process, I can use it for anything. I want to try to figure out, is there a way for me to do less work? Isn't that a good motivator? Hell yes. And there's so much symmetries possible. There's so much, because they're periodic at heart. So I shouldn't have to make a complete table for its entire period. I shouldn't have to do that very often. Sometimes I might, but I shouldn't have to do it very often. And if I know what the symmetries are, so if I know going in that something is symmetric with respect to the polar axis, I just have to graph points up here, and then I just mirror image the damn thing I just did, right? So how do I check to see if something's got symmetry with the polar axis? Let's start there. By the way, this is the last thing we're talking about is these types of symmetries. And get rid of all this crap here. Let me see if I can do that. Come on, go away. Do what I say. I'm sorry, computer, I didn't mean it. All right. So if I have a point, I just want to put a point somewhere. Well, let's see. Yeah, what the hell? So you have a point there. If it's going to be symmetric with respect to the polar axis, then it would have to then it would have to be down here. Let me see if I can't get a word out. So it would have to be like right here, somewhere right there, I guess. Yeah, looks about right. Yeah, right. So tell me. So if this point is r theta, I kind of put it off axis for a reason, so you couldn't really tell what it was. What's this point?
R negative theta.
Beautiful, right? If this is r theta, then this must be r negative theta. Can somebody even come up with another expression that would be the same thing, just to kind of push it here?
R theta plus 2 pi.
Oh, I like it. Okay. And then there's something even less basic here. What if I went, I don't want to say this, pi minus theta, and then I went negative r, right? Where would that be? Right here. And then I went negative r. I don't like that one. Screw it. All right. But I think you guys get the point. That we've talked about that before, about multiple ways to do it. And that actually is an acceptable way to check the symmetry. So how do I check the symmetry? Let's see here. How do I actually apply this idea? So in order to have polar axis symmetry, when you replace r and theta with r and negative theta, the equation has to be the same. So our equation up there was this. What was it? Cosine? Yeah. So if I replace r and theta with, I know it's kind of silly to say replace r with r, but we do. So replace r with r and replace theta with negative theta. What happens? What happens?
The negative goes away.
Negative goes away. Cosine eats it up, right? Because it's an asshole. So did I get the same equation back by putting our negative theta in? Yes. Therefore, it has polar axis symmetry. Any r as a function of theta where that's true has polar axis symmetry. Notice how slowly I'm talking. This is a good note to take. I don't know if you guys remember how to check even and odd symmetry. You plug a negative x in and you see what happens to the output. Isn't this a lot like that? What's interesting with polar coordinates is there's 3 types of symmetry. So let's talk about the next obvious one. That's one, and that's the test for it, is to use r negative theta. The next one would be, what if something had symmetry with respect to theta equals pi over 2? So the equivalent of the y-axis, which would mean if it's over here, let's just make this easy on myself. If it's over here somewhere, then it must be right there, right? Symmetric with respect to the y-axis, right? So if this is r theta, what's this? Oof. Ow.
Wouldn't it be negative r theta?
Be careful. Negative r theta would mean look at the same angle, but go backwards. So that would be back here. So let's do it. Let me make this, let's make it an actual angle. All right. So let's say I'm right here. So then the mirror image would be here, right? You with me? So that means that this reference angle has to be the same as this, right? So if this is r theta, what's this point? R
Pi minus theta.
pi minus theta. I like it, right? Another way to do this, now do you guys like, I don't like this as much. So what's another way to get to that same point? Maybe using negative theta.
Would it be negative theta and negative r?
I love it. So the test for theta equals pi over 2 symmetry. Oh God, in half, get in there. Is to replace, holy crap. What has today been like for Jeff? Apparently it's been rough. Replace r theta with negative r, negative theta. That would show you if it's got symmetry with respect to that. So a very simple one that does is r equal to 2 sine theta. Remind me, what does that look like? As opposed to 2 cosine theta. Anybody?
This one's fixed on the y-axis.
It's a circle fixed on the y-axis. I love it. And pretend like it's bigger. I can't remember. Circle fixed on the y-axis. So it should have this kind of symmetry. So let's see. Negative r equals twice sine negative theta. Do you guys understand? Replace r theta with negative r negative theta. And if you get the same as the original, it's got that symmetry. So sure enough, what happens on this side? What does sine do with this? It's a nice guy. So does he kill the negative? No, he can't do that. He's nice. He can't do things like kill things. So the negative's still there. See how anyway, sorry. And then the negatives canceled. Did I get the original back? Yes. So we already knew it had that symmetry, but it's a nice example of an easy example of something that has that kind of symmetry. And that's how to do the test. Okay, maybe. All right, and then let me see. What am I forgetting? What have I done? Let's see. I did polar axis symmetry, and I did pi over 2 symmetry. So now we got to do symmetry through the pole. I believe is the only one I got left. Let me see. Oh shit. Bum, 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 bum. All right, there we go. I'm doing this off of my memory, and this third one I have apparently forgotten. So let me see. Where are you? Should be right at the beginning. Hold on. There we go. What is this shit? Oh, they do. Okay, well, that's fine. Okay. Yeah, so this is kind of related to, do you remember what the definition of odd symmetry was? Why is it paused? What's happening with this?
It was f of negative x equals negative f of x.
Yeah, and actually be more specific, like even symmetry was symmetric with respect to the y-axis. Odd symmetry is with respect to the what?
To y equals x, right?
No, that was the inverse. This is the really weird one. It was with respect to a point.
Oh, to the origin.
To the origin. So that's exceptionally weird symmetry. This one is kind of related to that. It's the same thing. It's actually with respect to the origin. What happened? Oh, there I am. So it's with respect to the origin. So if I'm symmetric through the origin, that means that if I'm here, this is the most simple one, Jeff, and you forgot it. Yeah, I did. Then that would be the symmetric one. Whoo, Jeff. So if I'm at r theta, this is not bad at all. What would this guy be?
Negative r theta.
Yeah. So if you replace it with negative r theta and you come out with the same function that you started with, it's got origin, it's got what's called polar symmetry. What sucks is you got a polar axis and you got a pole. This is the pole, which kind of makes sense. Imagine this is the map of the flat earth. Sorry, this would be the North Pole. A little tiny sun going around and shining at a little spotlight. Anyway, sorry, I watched too many of those stupid videos. It's amazing. It doesn't bode well for us. So this is the pole. And this is the polar axis. This guy's a polar axis. Okay, so that's the difference. So this would be symmetry through the pole. If you replace r with negative r, and it comes out the same. So obviously something like r squared equals sine theta, right? If I replace r with negative r, it kind of course, it's got the same thing. You guys with me? Maybe, not really. Okay. Where did you guys go? There you are. All right. So very often, the very first thing you do is you see if there are any symmetries. If there are no symmetries, you will probably need to make a larger table. If there are some symmetries, so for example, these guys will always have symmetry with respect to the polar axis, right? Therefore, you only have to do from 0 to pi in your table, because then you can just copy it down on the bottom hemisphere, right? Bottom half. Does that make sense? If it's symmetric to the pi over 2, same idea, right? Same idea. You just focus on negative pi over 2 to pi over 2, and then you can copy it in the other part, and so forth. Hopefully that makes some sense, because the motivation is I don't want to have to make this stupid thing too big. Symmetries help you figure out how to make it smaller and get the whole picture still. Okay. I want to, yeah, maybe that's enough for today. You guys think it's enough for today?
Does the trigonomic function give you any clues on whether it would be on the polar axis or the pi over 2 axis if there's symmetry? Like
Yeah,
sines
you would
y,
expect.
cosines
What do you think?
x.
What do you think about something that's got primarily sine in it? What symmetry do you think it would most likely have?
The pi over 2.
Exactly. So that's a good point, Jason. You can, the functions that are present in something could tell you ahead of time which symmetry it's most likely to have, if any. But it's not like a good enough test by itself, right?
Right, but it kind of gives you a little bit of a starting point of something to think
Exactly.
about.
Perfect. Perfect. And of course, cosine would more than likely have polar axis symmetry, possibly, right? All right, cool. I love it. I think that's a good place to stop. We're about to get into things called parametric equations. After we do some more examples of these polar ones next time, we're going to get into something called parametric equations, which is so, oh my gosh. This is where I bring in the idea of an Etch-a-Sketch controlling the X and Y points. That might be more of a calculus thing. Oh shit. But it's the idea that both X and Y are controlled by another variable, which sort of sounds like a conspiracy, right? The the underground people that control the whole world. Anyway, that's what we're going to get into eventually pretty soon. Next time we'll do more examples of the polar graphs and the symmetry stuff. We'll do some funkier graphs and we'll check out their symmetries and we'll see what that means for our tables. All right, I think that's enough for tonight though. Let me know if you guys got to hang out, if you have any questions. Otherwise, you're free to head out or at least log off.
Thank you.
Which you're welcome.
Thank you.
You're welcome. Thanks for coming.
Hey, I had a question.
Yeah.
What again was the equation for pi over 2 symmetry?
Oh, so what you can always kind of recreate the idea. It would be like this, right? So if you're at r theta, now we did come up with one possibility being r pi minus theta.
Yeah.
But when you plug pi minus theta into something, it's kind of gross. It takes like an identity to figure it all out. You with me?
Mm-hmm.
So another way to get that same thing is to go negative theta, right? To go, how do I want to say this? I got to get my picture back here. I don't know if you're with what I'm saying at the moment. Where the hell did I put? There it is. Okay. I got to find you. Shit. Oh, too much technology. Okay, here we go. So let's see. We're talking about this guy here, right? So there was our first possibility. But that's kind of gross. So then we figured out it'd be much better to use negative theta, and then we have to look this way, but can go backwards. So it's negative r, negative theta.
Okay, so and an equation that would be able to do that would be what?
Oh, an equation that works for that?
Yeah, that would actually
Like the
produce.
2 sine theta right here. Yeah, like 2 sine theta.
Okay,
That's the most basic example of one that works for this.
got it. So
Now,
what are
something
we,
I didn't, go ahead, sorry.
oh, I was just going to ask, what are we going to be doing with these polar graphs beyond just graphing?
Well, all right. So if you're talking about in this class, not much. If you are taking calculus and maybe even calculus 2,
Yeah,
you'll
that's the
be
plan.
doing, huh?
I was just saying, yeah, that's the plan to go to
That's
calculus.
fine. Okay, then you'll be doing a lot more with these. You'll learn how to calculate the area of a cardioid by hand, for example.
Fun.
And if you can't draw it correctly, you won't have the correct bounds to work within. So, yeah.
Okay, got it.
Cool.